Okay, on to section 3.3. This bit of a lengthy section on the rank of a matrix. We'll run across inverses of matrices around the end of the section. Systems of equations will pop up in the discussion as well. Okay, recall the row space of a matrix A is the span of the rows of the vectors, the row vectors of matrix A. And the row rank of A is the dimension of this row space. The column space of A is the span of the columns, and the column rank is the dimension of this column space. Usual stuff from linear algebra. You'll also recall the dimension of the row space and the dimension of the column space are the same. Something I would be rather impressed with if you was proved in linear algebra. It, in my notes, pops up as Theorem 2.4 fairly early on when you encounter matrices, but I doubt you go through a proof of it in just in a sophomore level class. So what we're going to give here is a proof based in part on Gentle's argument in our textbook, and I went to another reference for a few more details. Peter Lancaster's Theory of Matrices is from 1969. I had it on my bookshelf. But we'll go through and establish that the dimension of the row space equals the dimension of the column space for a given matrix, and that common dimension, of course, is the rank of the matrix. Okay, first we need a lemma, a not surprising lemma, so this one has some intuitive plausibility to it. Take a collection of vectors, A super I equals 1 to k, and let the ith vector have components A sub 1 super I, A sub 2 super I, up through A sub n super I. So I need to talk about the components of each of these vectors. We're taking these to be vectors in Rn because you can see they have n components. And let pi be a permutation in the symmetry group S sub n. Then a set of vectors, A super I, is linearly independent if and only if the set of vectors given here is linearly independent. All right, so we're given k vectors. How they differ from the original vectors is by use of this permutation. We've permuted around the coordinates, the components of the given bunch of vectors. So for the first component, we don't have A sub 1 super I. We've got A sub pi of 1 super I. Whatever the image of 1 under this permutation is, that's what we're putting in the first slot, in the first component. So what we're doing is taking the components of all of these vectors and just jumbling around their components in the same way for each of those vectors. That is, permuting the entries in a set of vectors by the same permutation preserves the linear dependence and independence. The claim was, set of vectors originally given is linearly independent if and only if this new set of vectors is linearly independent. If and only if, so dependent for one implies dependent for the other. Okay, so that shouldn't be too surprising. Just all you're doing is uniformly moving the components around. So that's not surprising that that has no effect on linear independence. Let's go through a proof. Okay, there's a number of results in this section. Let's go through the first one. All right, so what we're going to do is actually turn this into a system of equations or reinterpret dependence relation as a system of equations, and then say, hey, with systems of equations, you don't care what order the equations come to you in. That doesn't affect the solution to the system of equations, and that's how we're going to deal with the permutation. All right, so take those vectors, A super I equals 1 to k. This collection of vectors is linearly independent if and only if, when we have a sum from I equals 1 to k, S sub I, A super I equal to 0 for scalars S1 through S sub k. This must imply that all those scalars are 0. All right. We want to show the same thing happens for this collection of vectors where we've permuted the components. Okay, so here's what we're going to do. So with that linear combination of vectors equal to 0, that implies, if we look at the jth component, I mean, we've got a linear combination of vectors. These vectors are from Rn. They're actually up here, they're written as row vectors. But if I look at their first components, then we have S sub I, A super I sub 1. And then we'd sum from I equals 1 to k. Must be the first component of the 0 vector. Must be 0. So what we're getting out of this for each of the components is a system of equations, or a linear equation, giving us a system when we look at all the components. So we get the condition, sum from I equals 1 to k, S sub I times A sub j super I equals 0 for j equals 1 to n. That's the condition on the jth components of both sides of this equation. Jth components here involve jth components of the A super I vectors. Over here, this is a vector on the left-hand side. That 0 on the right-hand side must represent the 0 vector. 0 vector where? Well, the A super I's are vectors in Rn, so this must be an n-dimensional 0 vector. Vector or scalar, it's clear from the context, they say, but they can be figured out from the context. So jth component on the right-hand side is 0. Okay, then we're getting this bunch of linear equations. These are numbers, right? S sub I, right, those were scalars. A sub j super I, that's the jth component of vector A sub I, has a number. So the right-hand side must be the number 0 as well. If you like, it's the jth component of the 0 vector given here. Okay, that is a system, j equals 1 to n, a system of n equations in k unknowns. The unknowns, you would think of it as the unknowns being the scalar coefficients, the S sub i's. So this system of n equations in the k unknowns, the S sub i's, has only one solution if and only if this system of equations given by sum from I equals 1 to n of k S sub I, A sub pi of j, A super I, or super I equals 0. So unique solution up here, if and only if unique solution down here. This is a system of equations. When I plug in j equals 1, I get the first one. When I plug in j equals 2, I get the second one. This is the same system of equations. When I plug in j equals 1, I get the pi of j's equation. But anyhow, I get the same bunch of equations. Different order, that's what the pi does. So we've taken the question from a question about linear independence of vectors and rewritten it in terms of a question involving systems of equations. The pi permutation, it just moves the equations around, changes the order of the equations, same collection of equations, so same solution. So unique solution up here, if and only if unique solution down here, namely that unique solution being all zeros. We're looking at a case of showing linear independence here, meaning we must be getting out those coefficients to be zeros. That is, we've got that unique solution if and only if the vector equation, sum from 1 to k, S sub I, B super I equals the 0 vector, where I'm just introducing the B's to represent these modified versions of the A vectors. So let B super I be the A sub I matrix with its coordinate, its components permuted around according to pi. Then I can say we've got linear independence with the A sub i's or A super i's, if and only if we've got linear independence of the B super i's. And that's really what we were asked to show. So set of vectors of the B super i's given by the permuted A's is linearly independent as well. So linear independence of these implies linear independence of these. If and only if, okay, that would be dealing with linear dependence. All right, I'd just go back, I'd look at a system of equations and I'd say, has a non-trivial solution, and carry that down to a linear combination of the B super i's set equal to 0 has a non-trivial solution. So I carry through that same type of argument. We go from unique solution where all the coefficients must be 0 to multiple solutions, one of which is non-trivial. Not all of the S sub i's are 0, and that carries over to here as well. So we get linear independent, linear independent, linearly dependent, linearly dependent. And again, not a surprise, all you're doing is permuting the coordinates around. But there's an argument for it, and a cute argument in a sense. We buried that permutation by looking at systems of equations and saying, hey, it doesn't matter what order you write the equations down in, the solution remains unchanged. Back to the notes for a theorem. That theorem is, let A be an n by m matrix, then the row rank of A equals the column rank of A. That common quantity, of course, is called the rank of A. So row rank was the dimension of the row space of A. Column rank was the dimension of the column space of A. Let's go through proof of that. Okay, so to prove that, some notation. Let's let the row rank of A be P, the column rank be Q. So we've got to call them something. All right, and we're going to do some permuting around. We'll quote theorems and stuff, but the manipulations we're about to do, they aren't terribly surprising. All right. Row rank of A is P. All right, fine. Rearrange the rows of A to form matrix B so that the first P rows of matrix B are linearly independent. All right, here's what's going on. In matrix A, you've got the rows spanning a space of dimension P, because P is the row rank. All right, that means there's a basis of the row space that contains P vectors. Dimension is the cardinality of a basis. Okay, well, you've got how many rows? A has n rows. Well, P of them are linearly independent. P of them form a basis for the row space. Collect those P together. Put them at the top, call that matrix B, and those other ones push them to the bottom. So that's what this means. Take P of the linearly independent rows of A and make them the first P rows of matrix B. Then push the remaining, n minus P, the remaining n minus P rows of A to the bottom of B. So we're keeping the same rows, we're just putting the linearly independent ones at the top. By the way, there's a permutation matrix P that would allow us to permute around those rows. We're just moving the rows of A around. Not going to affect anything in terms of row spaces. A and B have the same rows, so they get the same row rank, equal row rank. All right, now I want to talk about columns. All right, we're trying to link together row rank and column rank. By taking the rows of matrix A and permuting them around the way we did, if I'll consider what's happened to the columns of matrix A, whenever you're moved around two rows, you've interchanged components of column vectors. For example, if I swap the first two rows in matrix A, if I look at what happened to the columns, every one of the columns had its first component moved to its second component moved to the first one. You interchange the first and second rows of a matrix, you interchange the first and second components of the column vectors. So what we've done by permuting around the rows of A to create matrix B is we've permuted around the components of the column vectors of matrix A. And that's what we were just talking about, is permuting around components of a collection of vectors. That was the lemma we just looked at by lemma 3.3.1. The column rank of A equals the column rank of B. All right. The only difference between A and B, they don't have the same columns, but they got that permuted relationship between their columns. And that's good enough to say, okay, then all linear independent dependent relationships hold. If I look at the collection of linearly independent columns of A, by the way, that would equal the column rank of A. It's the same as the number of linearly independent columns of matrix B. Columns are different, but the number of linearly independent ones are the same. So what we're going to do is partition matrix B into two pieces, and looking for the linearly independent stuff. Take B, partition it as B1, B2 is given here, where B1 is involves the first P rows. It involves the linearly independent rows. And the remaining N minus P rows we'll put in B sub 2. All right, so what we've done from the beginning is take matrix A, move things around. So we got linearly independent rows at the top. Here, we're putting all those linearly independent rows in a submatrix B sub 1. Geez, what's a dimension of this matrix B sub 1? It has P rows. Number of columns would be the same as the number of columns of A. So it's what, M? So matrix B1, for the record, is a P by M matrix. And all the rows in B sub 1 are linearly independent. We made it that way. Not only that, but the remaining rows, the rows in B sub 2, they're not just any old thing. Each of the N minus P rows of B sub 2 are linear combinations of the rows of B sub 1. That's how they got to the bottom. They're linear combinations of the earlier stuff. We took the linearly independent stuff and put it at the top, and the linearly dependent stuff, dependent on those first P vectors, and put those on the bottom. All right, so that means if the rows of B1, say, are the row vectors R1 through R sub P, these are vectors, row vectors of matrix B1, and the rows of B2 are R sub P plus 1 through R sub N, so consistent notation, then each of these R sub P plus 1 through R sub N each of these are some linear combination of these. That is, for each L between P plus 1 and N, we can write R sub L as a linear combination of the R sub I's, where I ranges from 1 to P. Call those coefficients S sub Li. We're going to put those in a matrix here in a second. So I know, by the way we built things, the last bunch of vectors are linear combinations of the first bunch of vectors. All right, let the scalars in that linear combination be these S sub Li's as given. All right. Then I'm going to make a matrix, capital S, an N minus P by P matrix. Let the entries be those S sub Li's. Define matrix S to be the S sub Li's. I want to check real quick the dimensions. Let's see, we should have L ranging from 1 to N minus P, and I ranging from 1 to P. Let's back up and see. L ranges from 1 to P. Is that what I said? No, that's not right. I ranges from 1 to P. That's what I said. And L ranges from, it's subscripts over here, P plus 1 to N. Yeah, L range from P plus 1 to N. Oops, well, that's a range of N minus P. So the dimensions are right. The parameters are ranging over something else. I might need to adjust this, but we do get a matrix of that size. All right, so what we're going to do is take this matrix S, multiply it by matrix B sub 1, and by multiplying matrix B sub 1 on the left by this matrix S, we're getting linear combinations of the rows of B sub 1, and we're using the appropriate coefficients to produce the rows of B sub 2. So we get the matrix relationship B sub 2 equals S B sub 1. Remember, if I consider something of the form A times X, A is a matrix, X is a vector, those X entries become coefficients of a linear combination of the columns of A. Here we're multiplying on the left the B sub 1, so we're getting linear combinations of the rows of the matrix B sub 1. The way matrix multiplication affects entries in terms of linear combinations. It's a definition of the matrix multiplication that gives this. So we get B sub 2 can be written as S times B sub 1, meaning we're going somewhere with this. Matrix B can be rewritten not as B1, B2 is the partition, but B1, S times B1. Okay, so I can kind of more explicitly see the linear dependence when we write it like this. What we claim now is that the column rank of B is the same as the column rank of B sub 1. Okay, so let's take S, a vector, I mean, unrelated to these S's up here, just a new vector, column vector, write it as a row vector and transpose it, fit it on the slide. A column vector with components S1 through S sub m. Suppose we take S as that vector and we have B, matrix B times S equals 0. Matrix B we've partitioned like this. We're multiplying it by vector S and getting out 0. Well, think what happens when I do the multiplication here. We'll do row times column. Remember S, I took to be a column vector. Row times column, row times column, row times column. We could equally well just take that S and deal with this resulting matrix as being partitioned like this. We'd still do a row times column thing. We just get them inside the partition of the matrix instead of a partition times another matrix effectively. But multiplication gives us that we can rewrite this matrix product involving a partition matrix as this partition matrix. And out of this, we're getting 0. So we get B times vector S to equal 0, if and only if we get this stuff here to equal 0. Well, the only way this stuff here can equal the 0 matrix is if B1 times S equals 0. If B1 times S equals 0, we need that for the upper part. Also, if B1 times S equals 0, then we get the upper part to be 0. The lower part, well, yeah, if B1S is 0, then the lower part's going to be 0 as well. So we do have an if and only if relationship here. That is, B times arbitrary vector S equals 0, if and only if B1 times arbitrary vector S equals 0. So, linear combinations of columns of B, which this is, by taking a matrix and multiplying it by a vector on the right. That's a linear combination of the columns, kind of as I commented earlier when looking at this multiplication on the left by matrix. But this gives a linear combination of the columns of this thing. This thing is B. So a linear combination of columns of B is 0 if and only if the corresponding linear combinations of columns of B1 is 0. That's these two this observation translated into a comment about linear combinations of columns. Okay. So that's a comment about linear dependence and independence of columns. So the column rank of B is the same as the column rank of B sub 1. All right, so each of these, and we got into this mess, it brings back up the column rank of A. We set this up where we had matrix B having the same, the column rank of B is the same as the column rank of B sub 1, right. And so the same as the column rank of A, right? We commented above using the lemma that the column rank of B was the same as the column rank of A. So that's how it's all glued together. All right. So we've got, so we're going to concentrate on B sub 1. That's the nice little one. The columns of B sub 1, excuse me briefly, column rank. Yeah, okay, column rank of B sub 1 is the same as a column rank of A. We denoted that as Q. Q was just introduced as a symbol. So let's see, we've got Q, linearly independent vectors, column vectors in B sub 1. And let's see, these columns coming out of B sub 1, these are vectors in RP. Remember, B1 consisted of P rows, so we're getting these vectors in B1 alone to be vectors in R sub P. We know that those columns form a linearly independent set of Q vectors. Well, if you take vectors from RP and they're linearly independent, you can't have more than P of them and have them linearly independent. So the number of linearly independent columns of B1, that is Q, must be less than or equal to P. So we went through this argument to get that the row rank of A is less than or equal to, I'm sorry, the column rank of A is less than or equal to the row rank. That's what we got out of that. We could interchange roles here. We could probably also consider transposes. We could partition the columns up. We had a real angle of partitioning up rows up here, but we could rearrange the columns of A and create maybe a C1 and a C2 side by side, partitioning up the columns of matrix A, and do the same type of argument, ultimately to draw the conclusion that P is less than or equal to Q as well. So Q is less than or equal to P, as we showed. P is less than or equal to Q. Similarly, by playing with columns instead of rows, drawing the conclusion that P and Q are the same, the row rank of A and the column rank of A are equal. All right, and that common value is called the rank of a matrix. So there's something I doubt you did in sophomore linear algebra. Okay, with this established, we can make a bunch of observations. This lets us, in some crude sense, deal in a democratic way with either rows or columns. Well, in terms of dimensions of row spaces and column spaces, maybe. I can say things as follows. A quick little notational observation. We use this kind of calligraphy V of A, like the space of matrix A, I think Gentle may have called it. It was notation for the column space. So V of A denotes the column space of A. This is page 41 of the book we're using. All right, so if we took V of A transpose, that would be the row space of matrix A. So from what we just had, we see that the rank of A, well, that's the dimension of the column space, if you like. It's also the dimension of the row space. So the rank of A equals the rank of A transpose. The dimension of the column space equals the dimension of the row space. So this common thing, this common parameter of rank gives you dimension of the row space, dimension of the column space. I can relate rank of A to rank of A transpose, because there might be something you did see in sophomore linear algebra. Because what is the rank of A? Dimension of the column space, by definition, say. Then the rank of A transpose, well, the column space of A transpose is the row space of A, because the rows and columns have been interchanged. So the dimension of the row space, column space, you know them to be the same. So that's the reason the rank of A equals the rank of A transpose. How did you compute ranks? Well, a lot of this stuff's a bunch easier to remember if you think how you computed ranks. To compute the rank of a matrix in linear algebra, you row reduced it and you counted pivots. So if I row reduce a matrix and count pivots, or I row reduce its transpose and count pivots, you're going to have the same number of pivots. You also use the location of those pivots to find bases for row spaces and column spaces. Something a bit computational. I don't think we're going to encounter something quite that much computational in here. This is a touch more theoretical. You could relate rank to invertibility of a matrix, which the following will remind you of, though it's not being stated in the way you might think from linear algebra experience. A matrix is a full rank if its rank is the same as its smaller dimension. All right, like I said, when you calculated ranks, you row reduced and you counted pivots. Pivots were the first non-zero entries in the rows when we had the matrix in row echelon form or reduced row echelon form. Well, how much room is there for pivots? I mean, how many pivots could there be? If it's the first non-zero row entry, there can't be more pivots than there are rows. So the rank couldn't be any bigger than the number of rows. Also, each pivot's going to occur in a column. So there can't be more pivots than there are columns either. There just ain't room for more pivots than there are rows or columns. That's a way to remember this. I mean, the definition is what it is. But they say full rank and they compare it to the smaller of a matrix's dimensions. So a matrix is a full rank if the rank equals either the number of rows or the number of columns, whichever of those two is smaller. It couldn't equal the larger one if they're unequal. A matrix that's not a full rank is said to be rank deficient, and the rank deficiency is the difference between its smaller dimension and the rank. So how far is the rank from the smaller dimension? Remember how you compute these in linear algebra. Might have called that nullity at some point. That would correspond in a conversation about columns, say, to pivot-free columns. And you encountered this stuff probably in the setting of systems of equations. We'll do systems of equations here in this section before it's over with. But all this new vocabulary, if you think, I mean, even in linear algebra, if you think how you compute this stuff, it's way easier to remember the ideas. The vocabulary is pretty intense because there's a lot of it in linear algebra. We got a lot of it here, and they're using some different words in this book as well. But this rank deficiency might kind of remind you of the nullity of a matrix that we saw in the past. If you think how these are computed, it's certainly correct. A full rank matrix, which is square, is called non-singular. Okay, so full rank and square, non-singular. A matrix which is not non-singular is singular. All right. When you hear the word singular matrix, you should be thinking it's a bad matrix because it's non-invertible. Non-singular matrices, square ones, are good matrices because they're invertible. So from your past experience, you're probably used to thinking about singular and non-singular in terms of not invertible and invertible. Here it's been defined in terms of rank. Later we'll fix that. I guess it's note 3.3.a below. We'll use this idea of singular and non-singular versus full rank and not full rank and link that together with invertibility. And technically we haven't dealt with inverses of matrices in here just yet. Theorem 3.3.3 says, if P and Q are products of elementary matrices, then the rank of matrix PAQ is the same as the rank of matrix A. All right, let's see. P and Q are elementary matrices. That means they're or products of elementary matrices. That means they're products of matrices that involve, in a sense, the three elementary row operations. So let's go through a proof of that. This is another one of those where hopefully you see the proof, you'll think, oh, well, that's not a surprising result. All right, but we're going to have to talk about elementary matrices. Deals with products of elementary matrices. We're going to show the result holds for P, a single elementary matrix. And there's three different kinds. The result for Q, a single elementary matrix, will follow similarly. So we're going to look at multiplication on the left. That corresponds to elementary row operations. If we looked at Q and multiplication on the right, that corresponds to elementary column operations, and the argument will be similar. We're doing this for single elementary matrices. If you had products, bunches of them, we could get the result by induction. If I had several elementary matrices on either side, we can inductively show if the result holds for one matrix, then it holds for a product of several. All right, so remember, little notation, this is my doings here, of a elementary matrix of the form E sub PQ that resulted from taking the appropriate sized identity matrix and interchanging the pth row and the qth row. I denoted that E sub PQ. All right, if you do that to a matrix, do you think that's going to change its rank? Of course not. What's the rank? Say, let's talk row spaces, because we're looking at P and multiplying on the left. That's just so row operation-ish. So let's talk row spaces. We could talk either one, we know after what we just established. Row space, column space, same dimensions. So let's talk row spaces. So the rank of A would be the dimension of the row space of A. The rank of this elementary matrix, E sub BQ times matrix A, would be the dimension of the row space of this product. But wait, the rows of matrix A are the same as the rows of this matrix. The only difference is they're in a different order. So no surprise, the linear independence is all going to be the same. Linear dependence is all going to be the same. You got the same row vectors, they're just in a different order. Kind of similar to some other stuff we saw. All right, so E sub PQA has the same rows as A. So the span is the same, the dependence relationships are the same, the rows are just in a different order. So the rank of this elementary matrix, E sub PQ times A, is the same as the rank of A. Same rows. All right, for first elementary row operation, second elementary row operation, I denoted E sub SP. We took the pth row and multiplied it by non-zero scalar S. So if you'll do that to the n by n identity matrix, that'll produce one of these E sub SPs. My notation again, S is the scalar, P is the row that's affected. Up here I had an E sub PQ. Well, that's when we interchange P and Q rows. And a third is when we'll add a multiple of one row to the other. All right, so this is the elementary matrix we need to consider now. All right, the next two arguments are going to involve, all you've done is taken the pth row and multiplied it by S. That ain't going to change anything in terms of dimensions. That ain't going to change anything in terms of independence and dependence, which is why it doesn't change anything concerning dimensions and bases. All right, so let's see. Let R1 through R sub n be the rows of A. Then when you take A and multiply it on the left by this elementary matrix, you get a matrix with rows, R sub 1 through R sub n, except for the pth row that's been multiplied by scalar S. All right, so we're going to address this by looking at linear dependence and independence. Consider a linear combination of the rows of A. All right, so that'd just be equals 1 to n, S sub I for the scalars, row sub I, row R sub I. We could rewrite that as a sum from I equals 1 to P minus 1, plus a sum from I equals P plus 1 to n of the usual stuff. And what we could do is modify things a little bit in the pth entry, from P minus 1 to P plus 1, skipping over P. We'd have S sub P, R sub P. Yeah, but I want to relate that to this collection of vectors. So if I put an S, R sub P here, to keep the books balanced, I'll have to divide the scalar up front by S. I can divide by S, right? Right, it's non-zero. That's part of the story with elementary row operations. Okay, oh, and then the s's would cancel, and sure enough, we get equality here. But I want to look at this as a linear combination of the rows of matrix A, and this is a linear combination of the rows of E sub SP times A. Well, the only time all these coefficients are going to be 0, all these S sub i's are going to be 0, is when all these coefficients are 0. Of course, these are the same. Then we'd need S sub P to be 0, so S sub P over S would be 0. If some of these are non-zero, then some of these coefficients are non-zero. So if we've got linear dependence on the R sub i's, we've got linear dependence on these other things by just tweaking that P vector by multiplying it by S. We get the same dependence-independence relations between this collection of row vectors and this very slightly modified collection of row vectors. So the ranks are the same. And we'll do a similar type thing for the third elementary row operation. That third row operation being, take the rth row and add to it S times, say, the qth row. A little error there. It should read R sub P plus S times R sub Q. Okay? So I denoted that E sub P SQ to the Pth row. We're adding S times the Qth row. My notation. All right, so the rows of A, say, are R1 through R sub N. The rows of E sub PSQ times A, R sub 1 through R sub N, except the Pth one, which has become R sub P plus S times R sub Q, because, ignore that, that's the elementary row operation. Okay, well, let's take a linear combination of these and relate it to a linear combination of the original rows. I take a linear combination with scalars S1 through S sub N of these vectors. Okay, S1 times R1, S2 times R2, S sub P minus 1, R sub P minus 1. And then something interesting happens, and then the remainder of it is mundane. So, similar to what we had above, we'll write a sum from 1 to P minus 1 and a sum from P plus 1 to N. You just get the S sub i's and the R sub i's. And the interesting thing happens in the Pth slot. There, you get S sub P, but the vector has now become R sub P plus S R sub Q. So that's what we get for the vector. All right. I want to ultimately relate that to a sum from I equals 1 to N of S sub I, R sub I, the original rows of matrix A. But I'm going to take this to do so and rewrite it as given over here. All right. We've got I equals 1 to N, S sub I, R sub I. Here they are when I is between 1 and P minus 1. Here they are when I is between P plus 1 and N. And right here, there's what we get when I equals P. It's this thing that's extra. So on the right-hand side, let's rewrite this as a sum from I equals 1 to Q minus 1, plus a sum from I equals Q plus 1 to N, S sub I, R sub I. Everything's the same as the Qth one that's been messed up because you've picked up this extra S sub P times S, multiple of R sub Q. All right, yeah. You did that to the Pth row of A, but now I want to talk about the rows of the original matrix A. So that implies a modification of the coefficient of R sub Q, not R sub P. So we've got an S sub P times S R sub Q, S sub P times S R sub Q, plus somewhere in one of these two sums, there's an S sub Q R sub Q, S sub Q R sub Q. So the books are balanced. All right. I claim, well, this one's a little more complicated, we get precisely the same dependence and independence relations. If we set this linear combination equal to 0, and we were required to have S1 equals S2 up through S sub N equals 0, then on this side, you'd be required to have all the coefficients of R1 through R sub N equals 0. Yeah, for 1 through Q minus 1, be the same thing. And here, let's see, over here, if we had all those coefficients being 0, in particular, we'd have to have S sub P being 0. All right, if S sub P is 0, that drops from the conversation. Got a linear combination set equal to 0. We'll have to have S sub Q equals to 0. That's implied inside one of these summations as well. So in fact, this coefficient would have to be 0 as well. So we've got this collection of vectors, where we've got the modified pth vector is linearly dependent if and only if this collection of row vectors, the row vectors in matrix A, are linearly dependent or independent. So it's the same dependence-independence relation. It's the same thing we had above. It's a little more complicated because the indices get a little more shaken up in this one than they did in the first two. But we have the same dependence and independence relationships, so we have the same dimensional relationships, all of this being a conversation about rows. So the claim holds when we have a single elementary matrix on the left. All right, induction will tell you, you put a whole bunch of elementary matrices on the left, and inductively, you'll get the rank to remain the same. If we go to the right, same type of conversation, except now we'll replace all these comments about rows with comments about columns. We'll take the pth column and add S times a qth column to it. Same results will happen. Same dependence relations will hold on the columns, and we'll be able to draw the same conclusion if we look at the Q matrix on the right. Back to the notes. Okay. Let's see, super quick comment. Not a surprise here. The rank of the identity matrix is in. So we get from this theorem that if we take A to be I sub n, that each elementary matrix is full rank. We took A to be I sub n, the rank is n. If we then stick an identity matrix in here, we've got a product of elementary matrices times more elementary matrices. You got a product of elementary matrices. So every elementary matrix must be of rank n. Actually, every product of elementary matrices must be of rank n as well. Elementary matrices are good. They're good folks. They're invertible. They're easily invertible. Their determinants aren't hard to find. They're a full rank. Well, of course, if they're invertible, then they're full rank, but we haven't established that yet. You know that from your sophomore linear algebra days. All right, I've introduced as an exercise 2.1.g the following. Just some claims about dimensions of spans of vectors. This is back at the beginning of chapter 2, basically back at the beginning of the course. And those claims are, I mentioned these because we need them in proof of the following. If we take a set of vectors, n vectors, B a subset of set A, claim is the dimension of the span of B is less than or equal to the dimension of the span of A. Sure, you took a subset of the collection of vectors. I'd expect we'd get a smaller dimensional space to be shown in that exercise. If I take a given set of vectors A and break it into two pieces, say A1 union A2, claim is the dimension of the span is less than or equal to the dimension of the span of A1 plus the dimension of the span of A2. When do you think you get equality? Gee, talking dimensions, probably something about linear independence. I'd expect to be able to add dimensions when we get linear independence somewhere in the conversation. There's no hypotheses about linear independence, and we get an inequality there. If set of vectors A can be written as this direct sum A1, direct sum A2, that required that A1 and A2 be perpendicular. They were essentially disjoint. The only thing that A1 and A2 shared was a zero vector, if these were in fact vector spaces. and they are by hypothesis. So if we take A1 and write it as a direct, A and write it as a direct sum of A1 and A2, A1 and A2, all vector spaces, then the dimension of A is the sum of the other two constituent dimensions. Somewhere in there must be some linear independent stuff. I bring those up because we need those in proving the following. All right, so we're making a bunch of claims about ranks of partitioned matrices. Let's just go to the Beamer file. All right. So we're taking a matrix A and partitioning it into 4 pieces. And this looks kind of daunting with all the symbols. It's actually not so bad when you dig through the fog of all these symbols and see we're basically just talking about subsets of sets and spans. When I say rank, you may as well be talking about a span of a bunch of rows or columns. We get the same kind of behavior in terms of ranks, in terms of dimensions. So claim is partition A into these 4 pieces. The rank of any of those little 4 pieces is less than or equal to the rank of A, is the first claim. The rank of A is less than or equal to the rank of A11 partition A12, that's top part. I kind of want to call it the top row, but these are themselves matrices. Rank of A is less than or equal to the rank of the top part plus the rank of the bottom part. When I word it like that, it doesn't sound too outrageous. Rank of A is less than or equal to the rank of the left part plus the rank of the right part. Here, might want to think of row spaces. Here, I might want to think of column spaces because of the way the partitioning's been done. Remember the V represented column space? So it's saying the column space of A11, A12 transpose is orthogonal to the column space of A21 partition A22 transpose. If that holds, then the rank of A is the sum of the ranks of those 2 parts. And similarly, if the column space of A11, A21 is perpendicular to the column space of A12, A22, then we can add the ranks. So this last one involves summation of ranks, and equality also involves some orthogonality. The V indicates a column space. And that's the reason there's transposes up here in this first part. When we look at A11, partition A12, kind of thinking about these rows up here. When I put the calligraphy V in front, I'm talking column spaces. So we're transposing those rows so they become columns and then doing the addition, it looks like. Down here, that's not necessary because here we're looking at basically columns of the partition matrix. A11, A21, that's this first bunch of columns. A12, A22, that's this bunch of columns. Very much column space stuff. All right, so let's do the proof of that. First one. The rank of one of those 4 little things is less than or equal to the rank of A itself. Okay. Let's bust this matrix into pieces. The set of rows of A11, partition A12, is a subset of the set of rows of A itself. I don't think they gave us dimensions, but there's a first bunch of rows in matrix A. All right, that exercise we had above that I mentioned says, hey, you got a subset of the collection of rows, then the dimension of the subset, is the span of the subset, is less than or equal to the dimension of the bigger set. Here, the dimensions are ranks. They're ranks of matrices. The rank of a matrix is the dimension of its row space, right? Also, its column space. I want to talk about rows because of the way we're looking at the partition. So we can conclude the rank of A11, partition A12 is less than or equal to the rank of A. That's not what we're trying to show, though. We got too much stuff here. I need to get rid of this side or that side. Well, no big deal. We can do a similar type thing for the columns. If we look at the columns, A11, A21, this is a subset of the set of the columns of the whole matrix A. So again, by this little exercise, the rank of this is less than or equal to the rank of A. We could also draw a similar conclusion. This was the a sub 1 something. If we look at the a sub 2 something, the bottom half of that partition matrix, same argument, same conclusion. This was the left-hand half of the partition matrix. Second index is 1. If we look at the second index as 2, the right-hand half, same conclusion. All right. Now, a set of columns of A11 is a subset of the set of the columns of A11 partition A12. So now we're going to this little matrix here and saying, hey, if I just take the first bunch of columns, that's a subset of all the columns together. Okay, as argued above, that means the rank of A11 is less than or equal to the rank of the same bunch of columns with these extra columns thrown in. Similarly, for the rank of A12. So we're looking at the bottom half in this. So let's see, we can string this together. We're trying to show, say, A11, rank of A11 is less than or equal to the rank of A. Rank of A11 is less than or equal to the rank of this partition, and the rank of this partition is less than or equal to the rank of A. So the rank of A11 is less than or equal to the rank of A. So paste this together with that. A12, okay, we got A12 is less than the rank of A11, A12, paste that together with this, same conclusion. So that takes care of I and J being 1, 1, and 1, 2. Okay, so there's that conclusion. And then it just is similarly for the others. Yeah, same idea with the A21s and the A22s. If we'll look at what happens in terms of these columns, we can draw similar type relationships in terms of the partitionings there as well. So in the partition matrix, the rank of the little pieces is less than or equal to the rank of the big thing. Well, that makes total sense. I mean, if you think of the big picture, let's back up to the picture. Here we go. Sure. What, you want to talk about the rank of A? Say that's the span of the rows of A. All right, well, if I just took the rows that are up here in this little piece, that's less rows. So I would expect that the dimension of the space it spans to be less than the dimension of the space spanned by all of the rows. Now, there's a few details on there in terms of, well, the rows of A go all the way across, where the rows of A11 only go part way across. You know what I mean by the partition. But that's not terribly surprising that we get that kind of behavior, similarly with the other positions. All right, next claim. Rank of A is less than or equal to the rank of the upper part plus the rank of the lower part. Think of it like that, not surprising. Similarly, the rank of the left-hand part plus the rank of the right-hand part is greater than or equal to the rank of the whole thing. When do you get the inequality? Well, you know, I bet if we had linear independence, we'd get equality. So if we've got linear dependence, we might be up here counting the same thing twice. You know what I mean? To be informal about it. And that's when we get the inequality. Okay, let R be the rows of matrix A. Let R1 be the rows in the top part, this piece of the partition, and let R2 be the rows in the bottom part. Then R equals R1 union R2. Then disjoint union, I don't know, because I don't know anything about the rows of A. I don't know anything about the rank of A, other than the symbolic rank of A stuff. But we don't necessarily have these disjoint. One of the exercises I mentioned then says, hey, we've taken this set of vectors and cut it into this union, not necessarily disjoint union. Then the dimension of the span of this is less than or equal to the sum of the dimensions of the spans of the other two sides. Hey, the span of those rows is exactly the row space. Its dimension then is exactly the rank of the appropriate matrices. So there's part 3. Part 2. Part 3 is quite similar. So we'll break the columns into a first bunch of columns, C sub 1, a second bunch of columns, C sub 2. We'll get a union, same exercise. Same ideas, except now we're talking about columns, and that's a conclusion on part 3.